Now what we want to talk about is single slit diffraction. I want to talk about diffraction in general because we haven't mentioned that particular wave phenomena yet. And so what we get is that diffraction is the spreading out of a wave into the shadow region when it goes through an opening on the order of the wavelength. Of the wave. So what we're talking about is that if we were to open the door and then illuminate the door with light, then the light would come out and form an image of the door on the wall across the hall, and the size of the lit image of the door opening would be the same as the width of the door. Okay, so straight through, right? So I mean, if we have, here's the wall, here's the doorway, and if we, send light through, then what happens is it just goes in and illuminates this part. Okay, and you have that here. You would have two regions on either side where the light doesn't go into. But now what happens is you narrow the door so that the door opening goes onto the, down to the, on the order of the wavelength of the light. Then what happens is that the waves start moving out into the shadow region and then illuminate a greater region on either side of the, across from the opening. So as you narrow this, it spreads out. A very interesting feature. This is called diffraction. So, I mean, if we have a source of sound waves going through the door opening, then the sound waves will actually bend out into the shadow region, kind of like if it was, at the back door on a house. You can't see unless you're directly in line with the door, but you can hear just fine. Okay, because it'll bend out into the region beyond the doorway, the opening of the door. Okay, and so now what I want to do is I want to draw out the pattern for single slit, where it's going to have the same kind of geometry that we have here, and the same issue with the fact that it's not to scale. Okay, so if we go in and look for our single slit, and here's the slit, here's the screen. So you can see that the general setup's the same. This is why I usually like to talk about them at the same time. And then what we'll do is we'll mark in the width of the slit. I believe our book uses A. It could be W. It's another really common one. And then I believe again our book uses L as the distance between the slit and the screen. It could be R. It could be D. Whatever they're going to make it. Different books use different symbols. It's all the same dang thing. But ours is L. And then what we'll do is we'll plot positions along the screen. We usually mark those as Y. And then we draw this funny picture where we plot the intensity as function of position along the screen and superimpose it onto the image of where the screen is. What you'll see is that when we shine the pattern and it comes up on the wall, then it'll be just bright and dark along the wall itself. Okay, so you'll be able to see this type of feature. And so what we get is that our intensity is going to look something like this for the single slit. It looks something like it. Okay. And then our description of these pieces is that this is referred to as the central max. And then this is our first order max. This would be the second order max or bright spot. Okay. And then what we have is that this is the first order minimum. This is the second order minimum. And then the same over here. Now, we will mark our positions along the screen as Y, just as before. And then we'll mark from the center here out. This will be theta. And so we once again generate that same geometry because we will form a right triangle. So we get that the tangent of theta is y over L, or we could rewrite this as y is L times the tangent of theta. So if the angle's small, then the tangent of theta goes as theta, so then theta looks like y over L. And then previously we had that sine of theta was, well, d sine theta was stuff. M lambda or m lambda, m plus 1/2 on lambda. And so if you divide by d, then sine theta, small angles, goes as theta, but tangent goes as theta, and so then you can set y over L equal to m lambda over d stuff, and that applies the small angle approximation. So again, not a huge fan. It's not necessarily necessary. Then general, in many cases, they're applying the approximation before they know if it's valid or not, and so I don't know. Not a huge fan. Now, what we're going to find is that in terms of this particular pattern, we can get minima only. So we don't have a concise formula to identify where the maxima are going to be located, but it's just where the minima are going to be located. And the calculation's kind of interesting, okay, in that what they do is they go into the slit and they break the slit into the upper part of the slit and then the lower part of the slit. And then to calculate the minima, what you have is you have that the waves from the upper part of the slit should, in pairs, cancel with the waves from the lower part of the slit. So you have the wave that came out of this upper portion here would cancel with the wave that came out of that upper part of the lower portion there. And then in the middle of the upper part with the middle of the lower part, and the bottom of the upper part with the bottom of the lower part, and that they cancel, cancel, cancel all the way down. So now when we do canceling, then what we'll get is that our path length difference between the upper part and the lower part would then look like, A on 2 sine theta. My theta didn't come out very good. I'll try to fix it. A on 2 sine theta would be equal to our what? Odd half multiples type of thing. So some multiple of lambda on 2 types of things, right? I'm just making some heuristic argument. And then what technically happens is that the 2 here and the 2 there cancel. And so the formula we actually have is that A sine theta equals m lambda. And so I wanted to try to motivate why it's m times lambda and not m plus 1/2 lambda type of things. So it's not half multiples, it's integer multiples. But that's because we didn't use the full slit width, we used half the slit width. And when you multiplied over by 2, then the half ones went away and you get the whole ones. So that's my hand wavy argument. To do it better, we need to do other things. Okay, we need to do like a phasor argument. And that's just not what we're gonna do. So that would involve a whole class just to get over how to do the calculations and do the argument. So you're just going to have to take my word on it. But essentially it's because they bust it in half, and so they get A on halves, and then that half cancels the halves in the lambdas, and we get wholes. And this is the deal. Now, because they did this, then what you get is that your m values will only be plus or minus 1, plus or minus 2, and what you see is that there's no 0. Because if it was 0, we'd be here in the middle. We're at the center of the central max. And so 0 is not an option on this particular one. And like I said, when you do the big development and the big derivation, then it comes out nice and clean, you know, but I kind of wanted you to have a feeling for why it's m lambda and not like half wavelengths like we should have probably had. Okay? And so this will give us the locations of the minima only. And so then when we look at this, these are all real nice. This is m equals plus 1. This would be m equals minus 1. And this would be m equals minus 2. This would be m equals plus 2, and so on and so forth. So they all line up. There's not that issue with the offset that there was on the minima of the double slit. That all works. It's pretty nice, good stuff.